Alright, so this is chapter 7, which is all about light. Light is it turns out, related to electricity and magnetism, chapter 6 that we just had. Light is an electromagnetic wave. Well, it can be thought of as a wave. It can also be thought of as a particle. When light is called a particle, or thought of as a particle, it's called a photon. At any rate, light is definitely electromagnetic radiation, a form of energy, and it does, of course, interact with matter. We're going to explore that today. Alright, so this is just showing you what's going on. So there's an electric field that's waving back and forth in like a sine wave, and then perpendicular to that is the magnetic field that's in red right here, and the whole thing moves along in this direction at the speed of light. No matter what type of wave it is, or sorry, not type of wave, but no matter what type of form of electromagnetic radiation, which turns out to be lots and lots of different forms, including radio, microwave, the visible spectrum that the human eye can see. Alright. In fact, this is showing you the entire electromagnetic spectrum. We're not going to use this term millimeter waves. Nobody does. But let's start with the order that I want you to know this in. From the shortest wavelength. We'll get to what wavelength is shortly. But from the shortest wavelength, or the greatest energy, that means the same thing, or the greatest frequency. So the gamma rays have the greatest frequency, they have the greatest energy. It requires much more energy to create gamma rays than, for example, microwaves. And they have the shortest wavelength. They're the smallest in terms of their wavelength. Then comes X-rays, then comes ultraviolet, then there's the visible spectrum. Notice the visible spectrum, the greatest energy for the visible spectrum is in the deep blue or violet area, and the least energy as far as the visible spectrum goes. Notice the visible spectrum is just a small part of this entire electromagnetic spectrum, but the visible, the red is the least energy compared to the blue. And then comes the infrared, and then comes microwaves, and then comes radio. We're not going to distinguish between long wave and short wave. Okay, so so that's the entire electromagnetic spectrum, and the different locations of it. You know, like where does X-rays end and gamma rays begin, is actually defined by the government. And all right, so. Alright, so the sources of light, you know, it turns out that, well, let's just look at this. Matter can constantly absorb or emit radiation, and it certainly does. When something is incandescent, it is glowing due to high temperatures. Alright, so let's move on. There's this phenomena called black body radiation, which has to do with when something is glowing on its own. Surprisingly, the sun and all the stars are perfect black bodies. That is, they're perfect emitters and absorbers of light. So if you shined a laser beam at the sun, it would completely absorb that energy. And so it's considered what's called a black body. So anything pretty much glowing on its own is a black body. And what these different curves are telling you is wherever the peak frequency is, or peak wavelength, it doesn't matter, but wherever the peak frequency is, or peak wavelength, that tells you something about the temperature. So in fact, if the peak is more towards the blue end of the spectrum, like this one, and then the peak, and you compare that to one black body that has a peak more in the red. The one in the blue has a higher temperature than the one in the red. Or if even it doesn't even have to be part of the visible, you could have a star, for example, that has a peak wavelength in the ultraviolet or a peak wavelength in the infrared. The one in the ultraviolet would be much hotter than the one in the infrared. Okay? All right, so we think of light, one way to think of it is a light ray, and that's looking at it as a photon. And we'll look at this. The wave model looks at the motion of waves, and this is really good for explaining what's called these different phenomena. Interference, where the waves basically interfere with each other. In some cases they enhance each other, some cases they cancel each other out. Diffraction is this phenomena where waves can actually bend around a corner, and polarization is the ability to block waves. Like Polaroids are like sunglasses are good examples of Polaroids. It's a filter essentially where it blocks we'll see it in just a little bit. It blocks the waves that are waving in different directions compared to what the polarization is. And then mirrors and prisms. Mirrors, of course, bend the light. Change the direction of the light. Prisms will break the light into all the different colors. For example, white light is composed of all the colors of the rainbow, which we know from prisms. And lenses, of course, bend light, like glasses, for example. All right. Here's an interaction. So light encounters this is called a medium. Some of the light could be reflected. Some of the light gets absorbed, so some of that energy might be missing. The light can be bent. This is what's called refraction, and some of the light might actually get transmitted all the way through, like light that encounters glass or light that encounters water. Some of the light will actually get through. All right. This is not that important. Let's skip that. Let's see. So this is the law of reflection for mirrors. This perpendicular to the surface of the mirror is called the normal. So notice that that's at a right angle. So whatever angle that comes in is the angle is measured from the normal. It's kind of funny. You'd think that it would be measured from the surface of the mirror, but see, mirrors can be curved. And so this normal can always be defined, even whether you have a flat mirror or a curved mirror. And so this is the basic law of mirrors. It's really simple. The angle of incidence, so that would be this, is equal to the angle of reflection. All right, we're not really going to do much with that. All right, so this is an idea of real images and virtual images. So if you're looking at an object in a flat plane mirror, that object has an image that kind of, if you're looking at the mirror like this and this object is way back here, you'll see what's called a virtual image. That is, there's nothing behind the mirror. It's not an Alice through the looking glass kind of world. You can't go behind the mirror and find this object, and so we call it a virtual object or a virtual image. Let's skip that. So here's the example. This is one of the first things that we're going to look at. So you have a ray of light that's coming in with some angle with respect to the normal. Now what's happening here is we're going from one medium to another, so air to water, for example. And so what happens is the light gets bent. It bends because well, it's actually the light is actually changing speed from one medium to the other, and so it gets bent. And because this has a higher what's called index of refraction, the water does, than the air, the light basically moves slower in the water than it does in the air, and so it gets bent in the water towards the normal. So you can see that that angle right here is smaller than this angle. All right, and we're going to use that in just a little bit. And of course, the opposite would be true for, you know, the water going from water to air. The angle would bend, you know, even more in the air. All right, so let's see. I'll just briefly talk about what's called the critical angle. This is the reason that this is important. Has to do with really the internet. The entire internet is based on this phenomena of the critical angle. So here's what happens. If you had some light source beneath the water, and you shined it up at the surface, you know, if you shine it directly up, the light would just leave. You know, would leave the water and go up into the air. But then if you shine it at different angles, suppose it was like a laser, there comes an angle which is called the critical angle, where the light would completely stay inside the water. Now, that, just because of the index of refraction out here is smaller than the index of refraction out there. Remember, index of refraction is basically how much the light bends. And it's how slow the light goes within the substance. So the greater the index of refraction, the slower the light. So in air, the light is faster. Anyhow, why is this important? It's really important for what's called fiber optics. And fiber optics is actually built this way so that the central coil, or sorry, the central piece of plastic, if you will, has a greater index of refraction than the plastic that is surrounding it. And why is this important? Well, fiber optics carries light. Light is used what we do is we encode information onto the light, and what fiber optics is it actually you can use this, and you can actually bend the light rate. You can, you know, the fiber optic cables can be bent basically, and the light will follow the bend. You know, if you have something, you know, like an S shape, it'll follow that. As long as you don't have too great an angle, there still has to be this critical angle, and you don't want to lose too much of the light. Like if you bend it greatly, you know, like at a 90-degree angle, you'll have problems. So you want to kind of, anyhow, that's more engineering than anything else. All right, so here's our first equation. The index of refraction, as I've been talking about, is the speed of light in a vacuum divided by the speed of light in a material. It's just a way of talking about different materials without talking about the velocity in the material. So, for example, in air, the speed of light is approximately what it is in space. In water, it's about 1.3. Now, there are different types of glass, of course, but on average, you know, you can have an index of refraction of about 1.5. But like I said, that can be very different depending on the type of glass. Notice diamond has a really high index of refraction compared to glass, and in fact, there's a reason that we value diamonds. And really it has to do with this index of refraction, surprisingly enough. What that does is it allows the light bounces around more in the diamond, or it has more time, I should say, to bounce around and inside of the diamond, and it gives the diamond what